Okay, the next part that we have to talk about is the ideal gas laws. There are three laws that are quite important. We're going to start with the first one, which is the pressure law. The pressure law is about heating a certain mass of a gas, put in a container, and measuring the temperature. So it's a study of how does the temperature affect pressure of a gas, an ideal gas, practically. There's one thing here, there's so many control variables that we have to look at. The main control variable is the volume. So volume has to be kept constant here. So we can have the same container where we just heat it up. So the heat, as you can see, is applied here. And the pressure is measured using a pressure gauge. If you look at this table, as the temperature is increased from 0 to 25 to 50 up to 100 degrees Celsius, the pressure goes up, which can make us have a prediction that temperature and pressure are directly proportional. To prove that, we have to make sure that the equation is right. Now, as you can see here, there's a column for the temperature to be in Kelvin, and that's the SI unit of temperature. So every time we have to use the gas laws, temperature has to be changed to Kelvin. And then we can check if the values of the temperature and the pressure, these two columns, apply the equation to get a straight line. How can we make sure of that? We have to apply the equation, which is P1 over T1 equals P2 over T2. So to prove that they are directly proportional, as you can see in this column, the pressure is divided by the temperature, and every time we are getting 366.3, which means it is true. This allows us to draw these two graphs. The thing is that when we put the temperature in Celsius, the straight line wouldn't start from the origin because the pressure wouldn't be 0 when the temperature is 0 degrees Celsius. 0 degrees Celsius is a regular temperature that can happen anytime. In any country, the pressure doesn't drop to 0 because pressure is 0 means the gas will literally stop moving. But when the temperature goes to 0 Kelvin, which is a very low temperature, that's when it's considered to the pressure to be 0. Now, I want you to know how to change from Celsius to Kelvin. You have to add 273 to the Celsius temperature in order to get it in Kelvin. Forget about the 0.15 at the end. 3 significant figures is good enough. So that's the equation that we're using. P1 over T1 equals P2 over T2. Units are very important to deal with. That's a sample question from one of the multiple choice questions. We have a car tire containing air. That's the initial pressure in Pascal. Its original temperature was 27 degrees Celsius. That temperature is raised to 42. The question is to find the increase in the pressure of the air tire. And here I am going to circle the word increase because that's a small trick that some students usually forget to pay attention to. The first thing that we can say that this is definitely P1. This is T1, and here I have T2. The thing is, there must be the first step. What is step number 1? Correct. Changing Celsius to Kelvin. So you have to change these temperatures. Once you have them in Kelvin, you can move on to finding the second pressure P2 using this equation. You plug in the numbers and you calculate the new pressure, which is 1.31 10 power 5. Now, if you think you're done, you only can score, this way you score 2 out of 3. To get the third point, you have to find the increase in temperature, which is the change. So you have to find P2 minus P1, which is going to be 1.31 times 10 to the power of 5. And then you subtract from it 1.25 times 10 to the power of 5. If you do this subtraction, I believe that the answer is going to be by 10 power 5 is a common factor. So you just have to subtract 1.31 minus 1.25. The answer will be 6 times 10 to the power of 3 Pascal. So that's basically about the pressure law. Now, the second law that we have to talk about is Boyle's law. Boyle's law is the relationship between pressure and volume. We know that to do this, the control variable here is temperature. in addition to the amount of gas particles. Now, to do this, we need a container to press it. So we change the volume and we measure the pressure using a pressure gauge at a constant temperature. Here, we need to know that as the volume decreases, there will be more pressure because the particles are going to have more frequent collisions because of the decrease in the area of the walls, and pressure is force over area. So as area decreases, pressure is going to increase. The equation that we are going to be dealing with is P1V1 equals P2V2. It's different than the first one since they are inversely proportional, not directly proportional, so I cannot use ratios, I have to use product. And the graph also is not going to be a straight line. The graph is going to be looking like a curve. We'll look at it in a bit. Here is the same thing. We have V1, we have P1, and here is V2. We are asked to the new pressure, so we're going to use P1 V1 equals P2 V2, and that's quite easy. You just find the new pressure is 2.5 times 10 to the power of 5 Pascal. Now the graph looks like this. Don't ever think that the pressure and volume, this is how you do inversely proportional. That's completely wrong. Inversely proportional looks like a curve between the two axes like this. It doesn't matter which one is on which axis, but pressure and volume are related like this. That's a challenge question that I've seen once on past papers, and this question says that there's a cylinder filled with helium used to inflate balloons. You know, these balloons, like in posters or somewhere else, you can buy the birthday balloons and they inflate them with helium so that they rise. Now they're saying that that jar or the cylinder has a volume of 0.006 meter cubed, and the pressure of the helium inside it is 2.75 times 10 to the power of 6. Of course, there's a very high pressure of helium because there's so much helium in the cylinder. But when you put it into the balloons, definitely there will be a lower pressure. As you can see, it goes from 2.75 times 10 to the power of 6 into 1.1 times 10 to the power of 5. So the pressure is less now. Why do we make the pressure less? Because we need to inflate so many balloons. So the pressure of the gas inside the balloon becomes less, so that the volume becomes so much bigger in order to inflate as many balloons as possible. They said the volume of each balloon, and that's a trick here, just to each balloon is 0.003 meter cubed. We need to know how many balloons can be inflated. Look, I've seen some students think that we already have P1 and we already have V1 and we already have also P2 here, and some people think that this is V2, but that's the mistake. This is not V2 because that's the volume of each balloon. P2 is the volume of all of the balloons because you are using the helium to inflate so many balloons. So the first trick is to find the new volume, which is using P1 V1 equals P2 V2. So to find the new volume, you replace P1, P2 and V1, you find V2, which gives us 0.15 meter cubed, which is much bigger than the volume of the cylinder itself, and we were already predicting that. So this volume now is supposed to be divided by the volume of each balloon to find how many balloons are there. But if you do that, you're also falling for one trick, and that trick is the fact that you can't take out all of the helium from the cylinder, because when you start taking the helium out of it, some of the helium will stay in it and can't go out, which is the last amount of the helium in the cylinder, because in order to take them all out, at some point the pressure in the cylinder will be equal to the pressure outside, and it's not easy to take that helium out of the cylinder unless you have a pump. So we are basically losing the volume of the cylinder itself because this will not go out. You can't make the pressure inside zero. They will stay inside. So the last step is to subtract the volume of the cylinder from that volume, because this here is a volume that you can't extract. It's going to be lost. So that's basically what you're going to get, 0.144. And then you divide it by the volume of each balloon. You get 48 balloons altogether. So if you do not do the last step, you're going to get 3 out of 4, because you are going to use this formula as 1 point to get the volume is 1 point. Subtracting them together and finding this is 1 point. So basically you're losing 1 out of 3 or 1 out of 4 depending on how the question is structured. So that's one thing I wanted to talk about. The last thing is the combined gas law. What if we don't have any control variables in terms of pressure, volume, and temperature? All of them are changing. So when the only control variable is the number of molecules and everything else is changing, like in the diagram here, you are compressing the cylinder, the pressure is changing, you might have different heaters, so different temperatures. What happens in this case? In this case, we have to combine all the laws that we studied, which are about which is proportional, directly proportional, and which is inversely proportional, to make one equation, which is here. All of them are put together, the pressure, volume, and temperature, to get this combined gas law, which is P1 V1 over T1, this one here, equals P2 V2 over T2. Again, no scientist slept and had a dream about this. This was basically made. If you can look at P and V, they are inversely proportional. That's why you have a product. Whereas P and T, there's a ratio, and V and T, there's also a ratio. So they are directly proportional. And this allows us to solve for a case when everything is changing altogether. You have a question over here. We have an air bubble leaving the seabed going into the surface. So let's say here is the bubble starting and it's going all the way up. At the bottom we have P1. It had a volume V1 and it of course has temperature T1. When it goes up, it's going to be V2, T2, and P2. Now, let's look at the given. The pressure at the bottom is, so P1 is 600, that's P1 here. Whereas the pressure at the top is 100,000 kilopascal, that's P2. Now, the temperature at the bottom, again, that's T1, which is 12. Whereas at the top, T2 is 23. And the volume at the surface is to be found. Whereas the volume when it left the seabed is 7, so that's V1, because V1 is when it left. And the question is to find V2. This makes it very easy. You just have to use the equation P1 V1 over T1 is equal to P2 V2 over T2. So we have to replace, right? 600 kilopascal, volume 1 is 7, and T1 is 12 degrees Celsius, right? Oh, of course not. I'm sure that you got the mistake that you cannot replace the temperature as 12. You have to change it to Kelvin. So you have to make sure that you found T1, which is 12 plus 273. And this makes it 285 degree Kelvin. And then the same thing for T2. You put them all together in the equation. I am going to leave this for you to find how much V2 is. So you guys can try this question. I just want you to know that it doesn't matter the unit of volume or pressure. You can keep it in kilopascal. You don't have to change it to pascal because eventually you can cross out the K from both sides. Even the volume, if it's centimeter cubed on both sides, you don't have to change it to meter cubed because the centimeter cubed can be crossed out from both sides. The only sensitive unit is temperature. It has to be Kelvin, like how it is here. Okay, so try this out. And guys, I've posted already an assignment for you. It's due Sunday, so you have enough time to work on it. It's already on Digital Campus. I'm going to post it now also on Edmodo. This PowerPoint is there as well, this video, and also there is a quiz, a multiple choice quiz. I want you to try it. All of these documents are on Digital Campus, and they're going to be on Edmodo soon. I'll be waiting for all of your questions on Digital Campus, on the forum I posted, or on any comment that you make on Edmodo. I'm going to be answering it as well. So please start working on this. Next time, I'm going to be talking about thermometers and about specific capacity, specific latent heat, and that's going to be on Monday morning. Till then, take care, stay safe, and talk later. Bye-bye.